Hello students, this is a video on section 13.1, curves in space and their tangents. So here we get to finally get back into more calculus stuff. So when we're talking about curves in space, we're actually representing them as vector functions. So we're talking about a particle and its position in space at time t. And that position in space is represented as r of t. So r of t is the position of the particle, at time t. So not only is it a vector, but it's a vector that changes over time, so it's a vector function of time. Okay, so you can imagine some kind of curve like this curlicue that I drew here, and then at time t, where t might start at 0 here and then go all the way to 1 over there, at time t, the vector function represents the location of that particle. Okay? And then the whole point of calculus is once you know the position of a particle with respect to time, you can easily figure out the velocity and the acceleration by taking the derivative. Okay, and that's where we get into tangents. Okay, so remember, position is r of t, and then you've got velocity, which is v of t, is actually the derivative of position. So that's dr dt. And the way you take the derivative of a vector function is you take the derivative of each component. Okay? And that's velocity. That's the velocity of your particle at time t. All right, so we're going to be working on taking derivatives of position function, and that gives us our velocity function. And remember, when you take the derivative, that actually gives you the slope of the tangent line. So here with a vector function, if this is our position right here, r of t, then you can think of the velocity as the tangent vector to the curve there. So v of t might look something like this. So it would be tangent to the curve. Because remember, the derivative is the same as the slope of the tangent line. So the derivative of a vector function is going to be the tangent vector to that curve. Okay? And then, of course, once you have the velocity, or basically the speed of the particle, then you can take the derivative of the velocity, and that gives you the acceleration. Okay, so that's written a of t. So a of t, or the acceleration at time t, is given by dv dt. So if you take the derivative of the position twice, then that gives you the acceleration at time t. Okay, acceleration at time t. All right, and that's going to be the tangent to the velocity, which can be hard for me to draw, but I think we get the basic idea. Because the velocity is actually a function of time as well. So if you take the derivative of that, that's going to give you the tangent to the velocity curve, which is the acceleration, or how fast the velocity is changing over time. Okay? So I know that's a lot, but these are actually a lot of fun. You're not going to actually have to draw any graphs here. You're mostly going to be taking derivatives. Okay? So let's see an example. Okay, so example. The position of a particle in the xy plane, the position of a particle in the xy plane at time t is r of t, okay, r of t equals t plus 3 times I. Actually, let me write it over here. There's not enough room. So r of t equals parentheses t plus 3 times I plus parentheses t squared minus 4 times j. Okay, so this is a vector function of time representing the position of a particle at time t. Okay? And they're giving us this information, and then they want us to find an equation in x and y whose graph is the path of the particle. Okay, so find an equation in x and y whose graph is the path of the particle. Whose graph is the path of the particle. Okay? All right. So, and then the other thing they want us to do is they also want us to find the particle's velocity and acceleration vectors at t equals 2. Okay, so then find the velocity, v of t, and acceleration, a of t, at time t equals 2. Okay, so it's a lot of instructions here. But we're going to start with the first thing they ask us to do, which is to find an equation in x and y whose graph is the path of the particle. Now the basic idea there is, remember that this is a vector function, r of t, and it has, because this one is just with the xy plane, it only has two components. This first component times I is the x component, and then the second component times j is the y component. Okay, so this one is the x component. X component. First component is your x component, and then your second component is your y component. And then if it was in 3D, then we would have a z component times k. But this one is just with the xy plane, so this one only has two components. Okay, so the reason it's important that you realize that this is the x component and that's the y component is they want us to find an equation in x and y. So they want us to get rid of t. So this is what they're really asking us to do here. What they're really asking us to do here is to eliminate t, because they want us to find an equation in x and y. So we need to somehow get rid of t. So how do we get rid of t? Well, we have to eliminate t. Eliminate t. And the basic idea here is, since this is the x component, we know that we can set this equal to x. Okay, because since this is representing x, we can say x equals the x component. So x equals t plus 3. So our first equation is going to be x equals t plus 3. And then our second equation is going to be the y component. So the y component is y equals t squared minus 4. Because this represents y. Okay? So our next component is y equals t squared minus 4. Now, the reason we have to eliminate t is they're asking us to find an equation in x and y, and they don't say anything about t, so you actually have to get rid of t. Now, the easiest way to eliminate t is to solve for t. Okay? So to eliminate t, you solve for t, and then you plug in. Okay, you solve for t and plug in. So you pick whichever equation is easier to solve for t. Like here, I find this first equation to be easier to solve for t. So I'll call this one equation 1 and this one equation 2. So if I solve equation 1 for t, I can just subtract 3 from both sides. And I get t equals x minus 3 for equation 1. Okay, so there we solve for t, and then so we have x minus 3 equals t. And now we can plug that in for t into the other equation. Okay, so I'm going to replace that t in the other equation with this x minus 3. So we're going to plug in x minus 3 for t into the other equation. So that's going to give us y equals parentheses x minus 3 parentheses squared minus 4. And it is important that you put parentheses around the x minus 3 since it has two terms. Whenever you have more than one term and you're plugging in, you always have to put parentheses around it. Okay? So all we did there was we solved for t on the easier equation, then we plugged that into the harder equation, and then we got this new equation. So y equals x minus 3 quantity squared minus 4. And then where do we go from here? Well, they want you to actually multiply this out using FOIL. Okay, so we're going to use FOIL here. Okay, so using FOIL, remember that x minus 3 quantity squared is the same as x minus 3 times x minus 3. So using FOIL, the first is x squared. The outer is negative 3x. The inner is negative 3x, so that's negative 6x. And then the last is negative 3 times negative 3, which is positive 9. So you should have x squared minus 6x plus 9 minus 4. Okay, so we have y equals x squared minus 6x plus 9 minus 4. Okay, and then we can combine like terms. So we have 9 minus 4 is actually 5. So we get y equals x squared minus 6x plus 5. And that was actually the first thing they asked for. So let me go ahead and box that. So they wanted an equation in x and y. So y equals x squared minus 6x plus 5. That's your equation in x and y. Alright, so remember that was the first thing they asked for. They asked for us to find an equation in x and y whose graph is the path of the particle. And so that meant we eliminated t by solving for t and plugging in. and then we get our answer, which is y equals x squared minus 6x plus 5. And you can actually plug this into GeoGebra if you want to see the curve of the particle. Okay, this one's going to be a polynomial function. Okay, so it'll probably have a basically a parabola type graph for this one. Okay? And then the other thing they want us to do in this problem is they want us to find the velocity v of t and the acceleration a of t at time t equals 2. So we got our equation in x and y. So that's done. Now the next thing they want us to do is find v of t. So find v and a at time t equals 2. So let's start with v. So remember that v is the same as dr dt, which means you actually just take the derivative of each component of your function v. Your function r. So you take the derivative of each component with respect to t. So even though they had us get this equation in x and y, we're going to be going back to our vector function. So our original vector function v, sorry, I keep saying v, I meant to say r. Our original vector function r of t is up here. So r of t equals t plus 3 times I plus t squared minus 4 times j. So we're going to be taking d dt, or the derivative of r of t, which we said was t plus 3 times I plus t squared minus 4 times j. Okay, t plus 3 times I plus t squared minus 4 times j. And how do you take the derivative? Well, you take the derivative of each component. Right, so this literally just means you take d dt of the first component, so d dt of t plus 3, and you're going to multiply that times I, plus d dt of your second component, so it's going to be d dt of t squared minus 4 times j. Okay, and then for I, we know that the derivative of t is 1, and the derivative of a constant is 0. So we're actually just going to get 1 times I. And then for the derivative of t squared minus 4, using the power rule, remember the derivative of a power means you bring the power out front and you decrease it by 1. So instead of being t squared, we're going to bring the 2 out front, so it's going to become 2t. So we're actually going to have 2t. And then, once again, the derivative of a constant like negative 4 is 0. So you should have 1i plus 2tj. And what we just found here is the derivative of the position. So that's actually our velocity. So v of t. Or you can just call it v. And remember that 1 times any number is just a number. So we don't need to write 1i, we can just write I. Okay, so that's our v. And then they want us to find v at t equals 2. So v of t at time equals 2. So v at t equals 2 is the same as v of 2. Okay, that's all that means. So since we already have a v of t, the v of 2 is going to be the same as v at t equals 2. So all we do here is we plug in 2 for t into this vector function. Okay, so it's going to be v of 2 equals I plus 2 times 2j, right? And 2 times 2 is 4. So we actually have I plus 4j. Okay, so I plus 4j is our answer. So that's our velocity at time equals 2. Okay, so that's basically the speed of the particle as well as the direction of that speed. Okay, and then the last thing we need to find is the acceleration, and then we need to plug in t equals 2. But we already have the velocity. We know that the velocity is I plus 2t times j. And we know that the acceleration, a, equals dv dt. Okay, so the acceleration, a, equals dv dt. So we just take the derivative of the velocity. We take the derivative of each component of the velocity. So we're really going to have d dt of 1 times I plus d dt of 2t times j. Okay? So that's going to be our acceleration. d dt of 1 times I plus d dt of 2t times j. But the derivative of any constant, like 1, is 0. So that's going to give us 0I. And then the derivative of 2t is 2. So you should have 0I plus 2j. And of course, if you have 0 times I, you don't need to write it. So for our acceleration here, we're actually just going to have our a of t equals 2j. Okay, a of t equals 2j. And then they wanted us to figure out what the acceleration is when t equals 2, when time equals 2. So we're actually just going to go ahead and plug in 2 here. So a at t equals 2 is the same as a of 2. But notice we don't even have a t for a of t. So a of 2 is still just going to be 2j. If we had a t, we would plug it in. But when we took the derivative that many times, there weren't any t's left over. So our acceleration at time equals 2 is 2j. Okay? So I know it's a lot of steps, but hopefully it's not too bad, particularly if you remember your derivatives. Okay, cool. So I wanted to do another example. Even though these examples are long, I feel like it's good for you to see them. So, new example. This one has new instructions. So, this one says the equation r of t, so that's our position as a function of time, equals 3 sine of t times I plus 4 cosine of t times j plus 9t times k is the position of a particle in space at time t. Okay? Is the position of a particle in space at time t. Now remember, it's in space here because there's 3 components. There's the x component, the y component, and the z component. So this is our x. This one is our y. And then our third component is z. So because there's 3 components, you imagine it in space. It's going to be a curve in space that the particle is following over time. Okay? And they want us to find the particle's velocity and acceleration vectors. So this is the position vector, and they want us to find the particle's velocity and acceleration vectors. Find the particle's velocity and acceleration vectors. Okay? And then they also want us to write the particle's velocity at time t equals pi as a product of its speed and direction. Okay? So then write the particle's velocity. Write the particle's velocity at time t equals pi as a product of its speed and direction. As a product of its speed and direction. Okay, so that took me a while to write down, but let's go through this. So we have an equation representing a particle at time t, and it has 3 components, x, y, and z. So it's going to be, this is representing the position of the particle in space at time t. Okay, that's our r of t. First, they want us to find the particle's velocity and acceleration vectors, which are just going to be the derivatives. Okay, the first derivative and the second derivative of position. Then they want us to write the particle's velocity at time t equals pi as a product of its speed, which is going to be the same as the length of the velocity, and its direction, which is going to be the velocity divided by its length. Okay, but we'll focus on that later. Let's go ahead and find the derivatives. So let's find the velocity and acceleration vectors. So we'll start with those. Okay, so remember that velocity v equals dr dt. dr dt. So it's the derivative of the position. And here we know that our position is 3 sine of t I plus 4 cosine of t j. So we're taking the derivative of 3 sine of t times I plus 4 cosine of t times j. 4 cosine of t times j. And then we have plus 9t times k. Okay, so plus 9t times k. And remember, to take the derivative of a vector function, you just take the derivative of each component. So first of all, we take the derivative of 3 sine of t. Well, 3 is just a constant, so it stays out front. And then the derivative of sine should be positive cosine. So for our first component, we should have 3 times positive cosine of t times I. Right? Because the derivative of positive sine is positive cosine. Okay? And then for the next component, the derivative of cosine of t should be negative sine of t. Okay, so our next component is going to be plus 4 times negative sine of t, because 4 is a constant, it just stays out front, times j. Okay? And that's because we're taking the derivative of cosine, which is negative sine. And then for our last component, for the z component, the derivative of 9t is the same as 9. Okay, so for our last component, we should just have 9 times k. Okay, and then for our middle component, we can go ahead and bring the minus out front. So instead of writing plus 4 times negative sine t, I'm going to go ahead and write the minus out front. So it's going to be minus 4 sine of t times j. And what we just found there is the velocity of the particle. So that's v of t. So I'll go ahead and box that one. That was the first thing they asked us to find, was the velocity. Okay? And then the next thing we need to find is the acceleration. But remember that the acceleration is just the derivative of the velocity. So that shouldn't be too bad. So we're just going to be taking the derivative again. So our acceleration, a of t, is equal to dv dt. So we take the derivative of each component of our vector function v up here. So for the first component, the derivative of cosine of t is negative sine. So we should have negative 3 sine of t times I. And then for our second component, the derivative of sine is cosine, but we still have a negative 4 in front of it. So for our next component, we're going to have negative 4 cosine of t times j. And then for our last component, the derivative of 9, because 9 is a constant, is 0. So for our last component, we have plus 0k. Plus 0k. Alright? But then, remember, if you have a component that's 0, it's standard to not write it. Okay? So that means we don't need to write the 0k in our answer. So our answer is going to be a of t. The acceleration is negative 3 times sine of t times I minus 4 cosine of t times j. And then you don't need to write the last component because it's 0. However, when you're doing your homework in my math lab, they do have you write a 0 in there. But if you were doing a real physics problem, they usually wouldn't have you write the 0. But I think in my math lab, you still have to type in 0 because there's a box there, so you have to put something there. Okay? So I'm going to go ahead and box this. And again, in my math lab, I guess you would have to write the 0, so I can go ahead and write it here. But that 0 is totally optional. If you wanted to, you could just not write it in a real problem. Okay, so we have the velocity and the acceleration now. And then the last thing we need to do is the new problem here. They want us to write the particle's velocity at time t equals pi as a product of its speed and its direction. Okay, as a product of its speed and direction. So what we have to do there is we need to write down the velocity, v of t. We know that that's 3 cosine of t I minus 4 sine of t j plus 9k. And we want to express that as the product of its speed and direction. So the speed of a particle, is the same as the length of its velocity. Okay, so the same as the length of v of t. So notice I put the vertical lines, which means the length of v. Okay, so first we're going to actually need to figure out what the length of v is. So the length of v is going to be, we need to take the length of this. However, remember that it actually asks us to find its speed at time t equals pi. So what we have to do is we have to plug in pi first, and then we're going to find the length of that. Okay, so the speed of the particle is the length of v, and we want to do it at time t equals pi. So that means it's actually going to be the length of v evaluated at t equals pi. Okay, so first what we do is we plug in pi for t, and then we work with that. Then we're going to take the length of that. Okay, so when I plug in pi here, I'm going to have 3 times cosine of pi times I. Okay, so 3 times cosine of pi times I for my first component. And then we're going to have minus 4 times sine of pi times j. Okay, so minus 4 times sine of pi times j. And then our last component is going to be plus 9k. Okay, so plus 9k. All right, so you should have the length of the velocity vector at time t equals pi. And all I did there was I wrote my length, which is the vertical absolute value symbol. And then we have, I'm plugging in pi for t. So we have 3 times cosine of pi minus 4 times sine of pi plus 9k. So each component is written down. And then what we need to do to take the length is, remember, the length is from the distance formula. So it's just going to be the square root of the sum of the squares. But you want to simplify it first. So what is cosine of pi? Well, if you don't remember the unit circle, you can always look up the unit circle online. You know, just Google it or whatever your search engine is, unit circle. And this one actually already has the unit circle right here. I think with Google they'll have a picture of it. But if you want to do, what were we doing? We were doing cosine of pi. So cosine of pi means we're at pi here, which is on the negative x-axis. And then remember that cosine is the x-coordinate. So cosine of pi is actually negative 1. So here we're going to be plugging in negative 1. So we have the length of 3 times negative 1 times I minus 4 times, well, sine of pi, again, either remembering it or looking at the unit circle, that's the y-coordinate. Sine of pi is 0. So plugging in there, we actually have negative 4 times 0 times j plus 9k. Okay? But when we simplify this, the middle component is just going to be 0. So we don't even need to write the middle component. And the first component is going to be negative 3. So we really just have negative 3i plus 9k. Alright, and then if we want to take the length of that vector, we do the square root of the sum of the squares. Okay, so that's going to be the square root of negative 3 squared plus, well, the middle component is 0 squared, which you don't even have to write if you don't want to. And then for the z component, we have plus 9 squared. Okay, and negative 3 quantity squared is going to give us positive 9. Okay, so here you should have positive 9 plus 0 plus 81. Okay, so the square root of 9 plus 81, which is the same as the square root of 90. Okay? And then with the square root of 90, you can simplify the square root if you rewrite it as root 9 times root 10. You could take the square root of 9, and we know that that is 3. So that means our speed is actually going to be 3 root 10. Okay, so the speed of the particle is going to be v of pi, the length of v of pi, and that's equal to 3 root 10. And then we want to, they asked us to actually express the velocity as a product of its speed, which we just found, and its direction. So I don't know if you remember direction from one of our earlier lectures, but here's our speed. So that's our speed, and then the direction. The direction is actually just equal to the velocity v divided by the length of v. Okay? And so if we want to find the direction at time t equals pi, we're going to have v of pi in the numerator. So this is going to be v of pi in the numerator. And then in the denominator, we're going to have the length of v of pi, which is the same as its speed. Okay, so the direction of a vector is the same as the vector divided by its length. All right, and we already calculated v of pi. We know that v of pi was negative 3I plus 9k. So that's going to be our numerator. So we have negative 3I plus 9k. Okay. And then our denominator, we just calculated. The length of v of pi is 3 root 10. So our denominator is going to be 3 root 10. All right, and of course you don't want to leave it like this. You need to actually distribute the 3 root 10 to each component. Okay, so I'm going to break this up into 2 fractions. So the first fraction is going to be negative 3 over 3 root 10 times I. And the next component is going to be plus 9 over 3 root 10 times k. And of course, we're missing our middle component, so we should probably write a 0 for that for my math lab, even though you don't have to in the real world. Okay, so what happens here is the 3's cancel for the first fraction. So for the first fraction, we have negative 1 over root 10 times I. Okay. And then for the second component, I'm going to go ahead and write 0, j, since you end up having to do that on my math lab. Okay, and then for the third component, 9 divided by 3 is 3. So we're left with a 3 on the top. So we should have plus 3 over root 10 times k. All right, so that is actually the direction that we just found there. Okay? So the direction of v is this. Okay? And so since we have the speed and the direction, they wanted us to express the velocity as a product of its speed and direction. Okay? So the velocity v is equal to its speed times its direction. And that's not a dot product, that's just multiplication. Okay, so the speed times its direction. So the velocity at time t equals pi is going to be let me write this a little better. The velocity v at times t equals pi is the speed at pi times its direction at pi. But we already calculated those. So to write our answer, we write the speed, which is 3 root 10. Okay? So it's going to be 3 root 10 is our speed times our direction. So our direction was negative 1 over root 10 times I. Negative 1 over root 10 times I. Plus 0, j. Okay. Plus 3 over root 10 times k. Plus 3 over root 10 times k. And I know that can be a lot of work, but it's good for you. You got to get that practice in. And notice here that you don't actually rationalize the denominators. So this is actually how they want you to write your answer. So for whatever reason, they don't want you to rationalize. Probably because if you distribute the 3 root 10, the root 10s cancel out anyway. Okay, so this is actually the velocity as a product of its speed, which is the 3 root 10, and its direction. So it's going to be the speed times the direction. All right, so that's the last part of that problem.